Welcome back to Electronics. This is Dr. Robinson. In this lesson, we are going to look at second-order filter circuits. In the previous lesson, you were introduced to second-order transfer functions. And our objectives for today's lesson are to introduce second-order filter circuits, circuits that can be used to implement second-order transfer functions. And we're going to look at how you design a second-order filter. Here I've drawn the circuit schematic for what is known as a Sallen-Key low-pass filter circuit. Sallen-Key refers to this topology, this interconnection of resistors, capacitors, and this op-amp. Now you can identify this portion of the circuit as a non-inverting op-amp amplifier that you've seen before, where the gain from the non-inverting terminal to the output is equal to 1 plus R4 over R3. Now if you used whatever circuit analysis techniques you preferred to solve for the ratio of V out to Vin in this circuit, you would find that that ratio has the form of a second-order low-pass transfer function. Now one way to arrive at this transfer function is to use a node analysis, writing node equations here at this node A and this node B, and you also use what you know about ideal op-amps, that the voltage at this terminal is equal to the voltage at this terminal because we have negative feedback. And we can solve for the voltage at this terminal using voltage division. V out times R3 over R4 plus R3 is this voltage because there's no current into this terminal, and this voltage is equal to the voltage at node B. Then with a lot of algebra and some algebraic manipulation, you could put that ratio of V out to Vin into this form. And in doing that, you have one, proven that this circuit topology implements a second-order low-pass transfer function, and you've also in the process determined the design equations. Because in your transfer function, the quantity sitting here in this position would be written in terms of the circuit element component values. So we would have an equation for F naught in terms of the component values. We would also have an equation for Q in terms of the component values. And they're given by these three expressions, where K is equal to 1 plus R4 over R3 because of this non-inverting op-amp. F naught is given by this expression, and Q is given by this expression. So if you wanted to design a filter with a given F naught, K, and Q, you could use these three equations to solve for the component values necessary to implement that transfer function. Now, those expressions are reasonably complicated, so what's often done is some assumptions are made about the parameters in the transfer function or the component values in the circuit. So here I've listed three special cases where we make certain assumptions to simplify those equations that we saw on the previous slide. In this case here, I'm calling it special case 1, we have fixed K, the gain, at a value of 1, and we're solving for the two capacitors in the circuit. Now an easy way to fix the gain at 1 is to let R3 be equal to infinity, and R4 to be equal to 0. In other words, we make R4 a short circuit and we make R3 an open circuit. So under these assumptions, we get two equations that give us the values of the capacitors in terms of the other parameters. Q and omega naught, the transfer function parameters, and R1 and R2, the circuit element parameters. And you can further simplify these equations if you assume that R1 is equal to R2. Now a second case is we again let K be equal to 1, but we solve for the resistor values rather than for the capacitor values. And the reason for this is in a typical electrical engineering laboratory filled with bins of resistors and capacitors, you typically have resistors with tolerances of 5% and capacitors with tolerances of 20%. So it's often easier to choose the capacitor values that you know that you have, and then find the nearest resistor values. So by putting in this form, you can do that. The only restriction here on this equation is that this quantity under the square root must be positive. And I've drawn that condition here. And you can also see that the way this equation is written, R1 and R2 are interchangeable. You solve for one by letting this be a plus sign. You solve for the other by letting this be a minus sign. But in the circuit, you can interchange the values. Special case 3 is where we let the R's both be equal to each other, and we let the C's be equal to each other. So R1 equals R2 equals R, and C1 equals C2 equals C. we get these two simple equations. So for a given Q, K is determined. Then for a given omega naught, we can pick a capacitor and solve for the resistor. Then we can determine R4 and R3 with this equation. Here I have drawn the circuit diagram for what's known as a Sallen-Key high-pass filter. You can see the topology is the same, the interconnections, but in this circuit, where we had resistors here, we now have capacitors. And where we had capacitors here, we now have resistors. And again, if you solve for the transfer function, node analysis would again work in this case. You arrive at a transfer function that has the form of a second-order high-pass filter, where K, F naught, and Q are given by these expressions. Here I've simplified the equations of the previous slide using two special cases. Special case 1, where we fix the gain K at 1 and we let the two capacitors be equal to each other in the circuit. We arrive at these two equations for R1 and R2. Special case 2, we let both R's equal each other, both C's equal to each other, and we get these simplified equations, where if Q is given, we now have K, then we can choose an R knowing omega naught to get C, and then we can find the values of R4 and R3 from this equation. Now these special cases do simplify the equations, but you're restricted in your circuit implementation. For example, this equation, it's a very simple equation, but once Q is chosen for the filter, K is fixed at the value of 3 minus 1 over Q, and that might not be desirable for your application. Here is a Sallen-Key bandpass filter circuit. The topology is similar, but there's been an additional component added from this node to ground, this capacitor C1. These two values are resistors like they were for the low-pass topology, but here we have mixed a resistor and a capacitor. If you solved for the ratio of V out to Vn, you would find that the transfer function has this form, a second-order bandpass filter transfer function, where K, F naught, and Q are given by these three expressions. And to make these expressions somewhat simpler, an additional parameter, K naught, has been introduced, where K naught is equal to the gain of the non-inverting op-amp amplifier, 1 plus R5 over R4. I'm just giving you one special case here for the bandpass design, letting all the resistors be equal to each other, equal to a value R, and all the capacitors equal to each other and equal to a value C, and you get these simplified design equations. This is the transfer function for a second-order notch or band reject filter. It has the property that its Bode magnitude plot, ideally, looks like this, where it rejects frequencies in this band and passes frequencies outside of this band. So two pass bands and a stop band here. You can see that its denominator is a standard second-order denominator, but the transfer function is formed by moving both the highest order term and the lowest order term to the numerator and summing them. Now this transfer function, there's no Sallen-Key notch filter topology, but it can be implemented using what's called a biquad or a biquadratic circuit. This transfer function has both a quadratic polynomial in the numerator and a quadratic polynomial in the denominator. And a biquadratic circuit's transfer function has this form. But rather than introduce a biquad circuit, what I want to do is show you how you can implement this transfer function using the filters that we've looked at earlier in the lesson. This transfer function can actually be thought as the sum of two separate transfer functions. We have one transfer function here, and we have another transfer function here. So we can write that this is equal to K times JF over F naught squared over the denominator plus 1 over the denominator. Now, what type of transfer function is this, and what type of transfer function is this? This would be a second-order high pass, and this would be a second-order low-pass transfer function. So a notch filter transfer function can be obtained by adding a second-order high-pass to a second-order low-pass filter. And you can see that. What if we look at the Bode magnitude plots of an ideal high-pass and low-pass filter? So here is an ideal low-pass filter. Here is an ideal high-pass filter. Let's add these two transfer functions together. In this region here, we have 1 plus 0 is equal to 1. In this region here, we have 1 plus 0 is equal to 1. And in this region here, we have 0 plus 0 is equal to 0. So overall, the sum of these two Bode magnitude plots gives us a Bode magnitude plot that looks like this, that of a notch filter. So to form this, we can use our Sallen-Key low-pass filter, our Sallen-Key high-pass filter, and we can apply these both to an op-amp summing circuit to produce the output, where the input, Vi, is applied to both the low-pass filter input and the high-pass filter input. This ratio of VO to Vi would implement a notch filter transfer function. So in summary, during this lesson, we introduced second-order Sallen-Key filter circuits and the equations that you use to design these circuits. In our next lesson, we will use those equations to design a second-order low-pass filter. So thank you, and until next time.